All right. Any questions about that? About the esterification? You've seen, like I said, you've seen this mechanism before when we did aspirin synthesis in lab. So it's kind of a good place to overlap. Now let's go back up to here and talk about oxidation, right? Let me point out another reaction up here too. This ether synthesis, right? Do you see how I converted with when an alcohol and an alkyl halide in the presence of a base? I converted the OH from a alcohol to an ether, and this is just a simple SN2 substitution. I think we did a reaction like this already. All right, let's go down to the oxidation part. So somebody give me your definition of a oxidation. What did you learn in GChem about oxidation?
Losing electron.
Losing or gaining electrons, or losing electrons, and then reduction is a gain of electrons. In organic, when we say oxidation, the definition is a little bit different. You either increase the number of bonds to oxygen, that's one way to define oxidation, is to increase the number of bonds to oxygen, or you decrease the number of bonds to hydrogen. Right? So that's how we define oxidation, is increasing the number of bonds to oxygen or decreasing the number of bonds to hydrogen. And then reduction is the exact opposite. Reduction means that you decrease the number of bonds to oxygen or you increase the number of bonds to hydrogen. Right? So reduction is the exact opposite of what's written here. All right. So let's look at the top reaction, right? And the first reaction is a Swern oxidation. So Swern or chromic acid. Let me write that down. That second reagent is chromic acid. All right. Either one of those is going to convert a primary alcohol into an aldehyde. Can you see that? So this is why is this alcohol primary? Why are we calling that a primary alcohol?
It's on a primary.
Yeah, it's on the OH is on a primary carbon, so it's a primary alcohol, right? So if I treat that under Swern conditions, then or with chromic acid, both of those reactions are specific for primary alcohol. They're able to convert primary alcohols into aldehydes. All right. Let me switch this right quick because I want to show you the reagents for the Swern. It's a sulfur reagent. It's like DMSO, and I'll just pull it up. You don't have to worry about the mechanism part, but I just want to show you the reagents. Because every time I teach this, I get the same question. What are the reagents? So you need DMSO, which is here. And you also need oxalochloride, right? So these reagents with an alcohol and then followed by a base, those are your reagents for Swern oxidation. So DMSO is one of them. You can tell I'm not right with my finger now. So DMSO and then oxalochloride. By the time I get done writing this word, class will be over. right? So oxalochloride and then DMSO plus a primary alcohol. Those are your conditions for the Swern oxidation, right? And it's still, you can look at the if you look at the primary alcohol. Let me go back to my iPad. If you look at the primary alcohol, what happened? Is that zoomed in too far? What happened to the alcohol? What did I do to it in the product? What do you notice that's different?
You split it up.
Say again.
You split it up.
Did I split it up? Let's see. So one of the things that's different. All right, let's look at what's attached to the alcohol, and that'll help it make more sense. You got 2 hydrogens here. Is that right? On that carbon, yeah.
Right.
Mm-hmm.
And you also have a hydrogen here on the alcohol. Is that right?
Mm-hmm.
In the product, though, look at the oxygen. The hydrogen that was attached to the oxygen is gone, and one of these hydrogens is also gone. You following that? So you actually lost, and this is in a non-technical sense, you actually lost H2. You lost a hydrogen from the carbon, and you lost a hydrogen from the hydroxyl group to give you your pi bond here, right? Do you see? And so we put a new pi bond in here. Can you see that?
Yes.
Well, that's too thick. Yeah, so we put a new pi bond in here, right? And then we lost H2. So that's basically how every oxidation works. You lose a hydrogen from the carbonyl carbon, which is the carbon that's attached to the alcohol, and you lose the OH proton, right? And in a nutshell, that's how all of these reactions work. And that's how you're able to oxidize the alcohol up to the carbonyl, right? So you'll lose, and then, right, you lose this is called a carbonyl proton. So you lose the carbonyl proton as well as the OH proton, right? And in doing so, what in essence, what do we do here between the carbon and oxygen? What type of reaction did we do? What type of reaction will always give you a pi bond in the product?
Elimination.
Elimination. So in essence, this is a glorified elimination reaction, right? And so that's what we did. So all of your alcohol oxidations happen through a similar route where you have to lose one of those protons or one of those hydrogens adjacent to the oxygen, and then you also lose the OH proton. But the OH proton, you lose that a lot of times real early in the process. All right, any questions about that? So either one of those will give you an aldehyde from a primary carbon, or primary alcohol, I'm sorry. So chromic acid or Swern, either one of those are going to give you an aldehyde from a primary alcohol. Right, and if you look over here, I gave you kind of a list. So if you have a primary alcohol, again, knowing your functional groups is going to be critical because you need to know what primary means and what secondary means, so on and so forth. So if you have a primary alcohol, that's going to convert into an aldehyde. If you have a secondary alcohol, that's going to convert into a ketone. And then if you have a tertiary alcohol, that doesn't react. Why do you think that's the case? If I have a tertiary alcohol that looks like this, so let's say terbutanol, why do you think that's not going to oxidize? What did we just say you had to do on the carbonyl carbon in order to oxidize that alcohol up?
You have to lose 2 hydrogens, and if it's a tertiary carbon, it doesn't have the extra hydrogen.
Right, that's exactly right. You have no carbonyl hydrogen here to remove. Notice I'm not saying carbonyl now. I'm saying carbonol. So that there's no proton there, no carbonyl proton, so you can't remove it, so you can't oxidize it. All right. Any questions about anything? Go ahead and ask. Now it's Friday. All right. So the other oxidation is with TPAP and NMO. TPAP and NMO is TPAP is an acronym that's short for tetrapropyl ammonium peruthenate. So it's a ruthenium type catalyst. Right? Ruthenium is a transition metal. So it's a ruthenium catalyst, and it's specific for a secondary alcohol. So if you have a secondary alcohol like this one, how do we know it's secondary? Somebody help me out.
Alcohol's on
The carbon is not substituted.
Yeah, the carbon right here, where the OH group is a secondary carbon. So it's a secondary alcohol. All right. So again, if you have a secondary alcohol, when you remove this hydrogen, right, and you generate that pi bond, that secondary carbon makes it creates a circumstance to where we make a ketone in the product. All right. And everybody should remember that what that functional group, that ketone functional group is. Yes or no?
Mm-hmm.
Yes.
All right. Right. Again, everything organic is kind of like Lego blocks. So all that little stuff that you probably thought was unimportant in part one is very important, because those little small fundamental details, they govern everything that we do. All the reactions are either nucleophile or electrophile type reactions, or acid-base reactions, or radical react. Everything is going to fall into one of those categories. Everything's going to fall into either addition, elimination, substitution, or rearrangement, right? All of these oxidations are in essence elimination reactions, because you are creating a pi bond in the product. All right. Any questions so far? Everybody all right? Anybody jumped off the boat yet?